Our next speaker just before the break is Kylie Sinclair. And Kylie is a master's student in the ecology department at Utah State, advised by Keisha Manlove. Her research focuses on factors driving bighorn sheep herd recovery after disease, and she's broadly interested in wildlife management. She'll be finishing up this fall and hopes to transition into a career as a wildlife biologist. That looks like she's looking for a job. Kylie, please go ahead and load up your presentation. Perfect. I can see it there. And you're speaking like Brianna, or do we have you there?
Can you hear me?
Yes, there you go. Perfect.
All right.
Go ahead.
That introduction. I will be discussing results coming out of my research, looking at drivers of bighorn sheep demography following pneumonia-related die-off events. At this point, we have a pretty good understanding of what is causing or how Mycoplasma ovipneumoniae, or MOV, is getting introduced into wild sheep populations and the immediate consequences of that introduction. We find MOV in domestic sheep, contact results in pathogen spillover, and the pathogen spreads through the wild sheep population, causing an all-age die-off, with mortality rates between 10 and 90% of the population. We understand a little less about what's happening after this initial die-off. Frequently, we're seeing that the surviving sheep recover from disease, but we still have these carrier ewes in the population that are harboring MOV asymptomatically in the upper respiratory tract. This becomes problematic when lambs are born into the population, as they're still susceptible to MOV. And we start seeing these high lamb mortality rates in excess of 80%. And this can persist in these populations for several years following that initial die-off, preventing them from recovering. We also see herds that after that initial die-off seem to be clearing the pathogen completely. We're not noticing these carrier ewes, and we're not seeing this persistent lamb mortality, which is allowing these populations to recover relatively quickly after that die-off. So we're trying to better understand why we're seeing these differences in demography responses following that initial die-off. So my research has been focused on trying to better understand what's happening in here. To get at this, I've been utilizing a data set from the Nevada Department of Wildlife, looking at demography of 59 bighorn sheep herds across the state. And this includes 43 years of aerial population counts and classifications, and information on 3 different subspecies: Californias in the Northwest, Rockies in the Northeast, and deserts all across the South. For health data, we have results from almost 3,000 PCR and ELISA results for MOV, and information on 15 MOV spillover events, which has led to 149 post-die-off herd years for analysis. For this particular model, we've been focused on looking at lamb recruitment as a response to many different hypothesized drivers of what's driving this post-die-off response in populations. So you probably recognize the schematic from earlier, but I'm looking at another subset of these as potential drivers of what we're seeing. To start off with, I looked at density in herd modularity, or herd substructuring. For density, we just used a lagged effect of population size. For herd modularity, my lab mate used GPS fixes from colored individuals to create these spatial use overlays. These just kind of show some subgroupings within the population. And then from these, created these networks to see how connected these subpopulations are within that population. And so for this, we're hypothesizing that the more stable substructures are and the less mixing individuals do between subgroups, the better lamb recruitment is going to be, because the chance for pathogen spread is reduced. Next, we looked at host genetics. And for this, we're using nucleotide diversity in water sense estimator coming from Josh Janner's work. And these are basically just metrics on genetic diversity within a population. For host behavior and phenology, we were focused on subspecies for our metric here. And there's a couple reasons we felt like this was going to be a good metric for this. To begin with, we know that Rockies and Californias tend to form subgroups of about 10 to 20 sheep and have a very compact birth pulse of only a few weeks. Deserts, on the other hand, form smaller subgroups and have a very broad birth pulse that can last for months, which could reduce the chance of spread amongst lambs. We also, when looking at our MOV PCR and ELISA results, we saw a very different trend between the different subspecies. We looked to previous studies that have been done in Rockies and other areas to get an idea of what we would expect to see in the years following a die-off. And we see that herd prevalence tapers off gradually through time following a die-off, and seroprevalence more gradually through time. You may also see prevalence drop off more sharply in the first few years, but still have this tail for several years following that die-off because of carrier use in the population. For seroprevalence, since these are just based off titer values and not necessarily an infected animal, you'll see this taper off a little bit more slowly. And also, even if there are just a couple carrier use in the population and the rest have cleared the pathogen, if that's still present and their immune system is still being challenged with it, it's going to keep that titer response elevated. So you'll see a much slower tapering off of this value. Due to small sample size, we didn't look at the Rockies for this one, but looking at the California sheep, we see that their populations follow this trend pretty closely. These points are by herd year of sampling events, and they're sized by the number of animals sampled. So these outliers are just ones where there's only a few animals sampled, but these large sampling events follow this trend line pretty closely for both prevalence and seroprevalence. When we looked at deserts, however, we saw a very different pattern. The desert's prevalence and seroprevalence both drop off pretty quickly within the first few years. We also see another interesting trend with seroprevalence. For our Californias, early on after the die-off, we've got close to 100% seroprevalence in those populations. And even 15 years out, they're still hovering around 60%. But our deserts, even at their peak, are only getting to about 60% seroprevalence. So we're definitely seeing a different response to the pathogen by subspecies. For pathogen community, for this model, we focused just on our ELISA and PCR results for MOV. And then finally, for environment, we looked at drought for a metric here. We kind of focused on lag drought, expecting the impact of drought on an animal to show or have an effect the following year. We also felt like drought could drive behavior in the different subspecies, particularly deserts. Water is a very limiting resource in the desert, and during drought, it becomes even more limiting, which could increase grouping and congregation and mixing between desert animals, which could increase the chance of pathogen spread, which could lower lamb recruitment following die-offs. So we used a Poisson model to look at, it uses an offset to look at lamb recruitment in the years following die-offs in these populations. And our model puts out this coefficient plot. And if the coefficient estimates fall across 0, this vertical line here in the center, it means the model's not detecting an impact on lamb recruitment. Anything to the right or above 0 is an indication of a positive effect on lamb recruitment, and anything to the left or below 0 is a negative impact. Starting with our herd density and substructuring metrics, density does have a positive effect on lamb recruitment, but it's very small. Even when we scaled it up to the addition of 100 sheep into the population, it's still a very minute difference. So there is a positive effect, it's just not overly noticeable. Our modularity metric does go across 0, but only just. So at this point, it's not statistically significant, but it does have a positive trend, which is what we expected. The more substructured a population is, the less spreading in between subgroups, which could reduce lamb recruitment or reduce the chance of lamb mortalities. So we want to do a little bit more investigation on that metric in future iterations of this model. Our genetic diversity, or host genetics, we had opposite effects that we weren't really expecting. And at this point, we're still trying to better understand what these metrics mean for the population. We're also wanting to consider these for pre and post die-off metrics, if there's a difference there, as well as considering some other alternative metrics. So at this time, we're not really sure what to make of this, but we're going to do some more digging here in the future. By subspecies, we find that our California bighorn sheep herds have poorer lamb recruitment when compared to deserts following die-offs. And for our pathogen community, both prevalence and seroprevalence had the expected trends that we thought we would see. As these increase, lamb recruitment decreases. which is also an indication that that seroprevalence or titer values is probably a good indication of carrier use still being in the population, presenting that pathogen to lambs. We had some interesting results coming out of our environmental covariate here. Lag drought actually ended up having a positive effect on lamb recruitment. We think the reason for this is ewes likely probably aborted fetuses early in their pregnancy during years of drought in order to focus on their own survival, which meant they actually had an entire year of focusing all nutrients on themselves rather than rearing a lamb, which meant they probably went into the following year in better condition, which would set them up for a better lamb recruitment year. So kind of an interesting result that we didn't expect to see. We also saw that drought had more of a negative impact on our California bighorns rather than our deserts. So even though we anticipated that deserts might have increased pathogen spread from more congregating during drought, it seems that in general, they're just more adapted to dealing with drought. So we are starting to see that there are some effects of different drivers, changing what we see for lamb recruitment following die-offs. So these are some good starts, we think, on understanding what's happening in these post-die-off years. And we'd like to move forward this model, better understand some of the metrics we have in here, dive into them deeper, as well as add in some new metrics like increase our pathogen community metrics and look at NDVI for environment. We're also in the process of setting up a ewe survival model focused on our individual data that's coming out of Nevada Department of Wildlife as well. And again, looking at these post-die-off demographic responses. Our goal for both the lamb recruitment and ewe survival models is that hopefully our results can help with management. We know that agencies do not have unlimited resources, and the ability to identify which herds are going to have more of a negative impact versus be able to cope with die-offs after a MOVI introduction will be really important for mitigation management efforts. With that, I'd like to thank the Nevada Department of Wildlife, particularly Mike Cox and Perry Wolf for their contributions to the data, as well as Josh Janner for his host genetic information. And for my own research laboratory at USU, particularly my advisor Kezia, and then lab mate Lauren for her adding in those herd modularity metrics. And with that, I can take any questions.
Thank you very much, Kylie. You two have helped catch us up. So we have time for questions right now. And I think we'll have a bit of time also for questions for the other speakers just before the break. So I'll let people throw some questions in there if they wish. And our first question that we have is coming from Tom Stevenson. Do you have any evidence that desert bighorn are aborting embryos, fetuses, or simply not ovulating and getting pregnant if they are in poor condition?
Not out of this data set. This has kind of been more of a broad data set. We're working on trying to get into the individual a little bit more with our next model, but at this point, no, I don't know about any of that.
Okay, great. I'm not seeing any other questions. Folks, if you're afraid to type and want to put your hand up, we can also manage that and you can actually speak. So I'll just. So we have a question coming in here from Mike Cox, depending on how nimble his fingers are. I could let you talk if you want, Mike.
Thank you, Susan.
There you go.
Yeah, I was going to mention for Kylie's benefit in terms of that herd modularity, when we have guzzlers going dry during the drought period, we'll have 10, 20 ewes that will leave. And then if we have a disease spillover, they're moving to another guzzler where there's probably 10 or 20 other ewes. And so I do think after the event, after the pathogen has made it into a herd, that drought is definitely going to help spread that pathogen.
Thank you.